So let's discuss some of the details that are involved with experiments 19 and 20, the reactivity of alkyl halides. So let's discuss some of the differences between substitution reactions. For these particular set of experiments, we're not going to be dealing with eliminations, so we're not going to be comparing substitution versus elimination. We're going to be looking at the differences between different types of substitution, specifically SN1 and SN2. So remember, when we use the term SN1, we're talking about something that is unimolecular, and that's where the 1 comes from. So unimolecular in the rate determining step. The S and the N are just substitution and nucleophilic. Now substitution is pretty self-explanatory. We're just swapping one functional group for another. Particularly, we're just in this experiment, we're taking a halide and converting it either into a different halide or swapping it for an alcohol or ether. And we'll talk about that in the mechanisms. So the substitution part, we're just taking a halide and swapping it. The nucleophilic, right? Remember what the term nucleophile stands for, right? A nucleophile is something that likes a positive charge. And so what that means is a nucleophile, we're going to be looking at things that have negative charges, either fully negative charge or partial negative charges. That's what we have to differentiate between when we're dealing with nucleophiles. So nucleophile. So unimolecular at the rate determining step. We're looking at nucleophile and we're doing a substitution. Now in SN2, right, the S and the N mean the same thing. The 2 just means bimolecular. And so that's going to affect our mechanisms, right? The 1 versus the 2. The key important difference is that we are forming a carbocation with SN1. I mean, that's not the only difference, but if we could say this is one distinguishing factor between the two types of substitution, it's that formation of the carbocation. And remember, the carbocation tends to be our slowest step, which makes it our rate determining step, and it is unimolecular because it only involves one molecule at that rate determining step. A bimolecular SN2, right, this is where we have a concerted reaction, right, it's concerted reaction, which typically means we only have one step in our mechanism, although there are exceptions. But what it means is that our incoming nucleophile and our leaving group are working in the same step, right? It is concerted, they're working at the same step, and if we have a leaving group and an incoming nucleophile working in the same step, that's where our bimolecular part comes from. Now, it would be in your best interest to go through and recap, read through your textbook about the differences between SN1 and SN2. This is just a brief summary. So looking at the left-hand side there, one of the key differences to indicate whether we are going through SN1 or SN2 is the sterics of the leaving group. Right, so the sterics of the leaving group. And remember, when I'm talking about leaving group, in this case, we're looking at the halide. The identity halide is going to play a difference also. Fluorine versus chlorine versus bromine versus iodine. They're going to have different, let's say, a different propensity for acting as leaving groups. And it all has to go back with how stable it is with that minus charge. Iodine is an excellent leaving group. It's a far better leaving group than something like fluoride is. So iodide, I minus, is a much better leaving group than fluoride is. And the question is, well, why is that? And so go back and take a look. It's going to have to deal with stability of that minus charge, right? That's one way we can look at it. So go back, review the identity of the halide and how that affects the propensity for it to act as a leaving group. Right below that is another key important step. It's let's call it the flavor of the halide, aka is it primary, secondary, or tertiary? A primary halide's going to behave very differently than secondary than tertiary. Remember, your primary halides are going to favor your SN2 mechanisms. Your tertiary are going to favor SN1. And your secondary is somewhere in between, so we have to look at some of the other factors involved with that. The incoming nucleophile is also going to have a big role on SN1 versus SN2. Weak nucleophiles tend to favor SN1. Strong nucleophiles tend to favor SN2. And again, the question might be, what is weak and strong? If we want to simplify it and put in a short statement, a weak nucleophile is something that does not possess a negative charge. A strong nucleophile usually has either a fully negative charge that's delocalized or a partial negative charge that's localized. So if we want to summarize the incoming nucleophile, let's say we're looking at the identity and the strength of the negative charge on the nucleophile. And below that, right, with the SN1, SN2, pay attention to your carbocation formations, right? Remember, we're not going to be forming primary carbocations. There's only a couple of exceptions to that. In general, if you're going through and you're writing a mechanism and you form a primary carbocation, make sure that you know what you're talking about and make sure it's in one of these exceptions. Generally speaking, primary carbocations are not going to form. But anytime we do form a carbocation, we have to pay attention to rearrangements, structural rearrangements. Do we have hydride shifts? Do we have methyl shifts or alkyl shifts or any of these other things that happen when we're dealing with carbocations? SN2 mechanisms, as we discussed, happen to be concerted, right? The rate determining step happens with a bimolecular species, the incoming nucleophile and the leaving group, and they tend to be faster. Now, when we're talking about faster in the realm of chemistry, we're dealing with kinetics. And so when I say faster, I'm talking about with respect to the formation of the carbocation. So we're comparing the rate determining step. It's not always going to be the case, but in general, to keep things simple, let's call SN2 reactions faster when we're dealing with the comparing SN1 versus SN2. So let's look at some of the mechanisms that we're dealing with for this experiment. So we're going to be looking at, right, and let's just let X represent any halide. So if we have a primary halide, and we're going to do a reaction where we add in a source. Whoops, let me just change this. We're going to add in a source of a different halide, right? So we have a red halide, we have a blue halide. And so what happens with our two mechanisms here? So what we want to do when we want to predict a mechanism for a substitution, let's take a look at our substrate, right? So here's our substrate. And what do we see? We see that we have a primary leaving group. Okay, so we have a primary leaving group. That is our big important flag to say likely we are going through an SN2 mechanism. Remember, as I said on the previous slide, SN1 mechanisms are not really going to be happening with our primary leaving groups. So we have a primary leaving group. Our incoming halide in blue there is a good nucleophile. Most of our halides tend to be good nucleophiles. So if we have a primary leaving group, a good nucleophile, we're going to hit that carbon, pop out our red halide there. And so our mechanism for this is pretty simple. Let me start to color code a little bit, right? We make that bond in green. It is bound to that incoming blue halide now. And we happen to spit out our red halide. Now in reality, this is a reversible reaction. So we could draw the reverse reaction, right? And then we could color code this in purple over there just to kind of follow along. So remember, our halides are good nucleophiles, so we could reverse this reaction. Now eventually this equilibrium is going to favor one side versus the other. And that's going to depend on not only our substrate, but it's also which nucleophile, which halide we're bringing in and which one acts as a better nucleophile. But for an SN2 mechanism, this is generally how they look, right? So here's an SN2 mechanism. Primary leaving group, incoming nucleophile, bimolecular in the rate determining step. If we change, right, and so now let's have a tertiary leaving group. Let's bring in our X minus again. Now we cannot do a SN2 mechanism. Tertiary leaving groups are too sterically hindered for a halide to come in and do a substitution reaction. So the first thing that's going to happen in an SN1 mechanism is that we're going to generate a carbocation. And that is something that it does by itself, and our solvent does affect that some. But it's just going to basically pop off, leave a carbocation behind. So our X minus gets formed. We still have our blue X minus around, so both of our halides are there now. And so now the next step in our mechanism can happen. We could bring in our blue halide to attack that carbocation. So let's draw that real quick. So our product in this case, right, we make that orange bond, and now it's bound to the halide there. And we still have our X minus around. And this is an example of an SN1 mechanism. So SN1. Now, just as we discussed with SN2, this is reversible. That X minus could come back in here also and generate that bond right there. So that step is reversible. And if we wanted to be complete about it, even this last step here, let's do it in light green, right? Even this step here is reversible also. Especially in the reactions that we're doing today, since we're swapping one halide to the other, we notice that all these steps are reversible. And so the first question should be, well, wait a minute, how are we going to control this then? And what we're going to do, and as you read through the book, we're going to control this a couple ways. By solvent, temperature, and by reaction. So if we use the right conditions for our reaction, we can actually take any of these X minuses that get formed along the way, right, and take them out of the reaction. We can precipitate them out. So we can use the solubility of the different halides, the solubility of the red halide versus the blue halide. We can use those to precipitate these things out of solution and remove them from our reaction. So if we remove our red halide from our reaction, then we are basically shutting down certain reverse reactions, right? So let's just show that, right? If we remove them from our reaction by precipitating them out, they are now a solid, and remember that solids are not involved in our equilibrium anymore. And if we don't have that there in our equilibrium, then we basically shut down some of our reverse reactions. And so then we basically only favor our reaction in one direction. And so when you read through your book, you're going to be looking at silver nitrate and how we can use that to determine some of our reactivities. And that's going to be based off of reacting with the different halides that are there and their solubility. So let's discuss two of the reactions that we will be accomplishing in this lab. So if you take a look at one of the parts, specifically in experiment 20, in experiment 19. So in experiment 19, we'll be using two solutions. We're going to be using a solution of silver nitrate. Now, silver nitrate is an ionic compound. So typically our ionic compounds are going to be soluble in water, especially our simple ionic compounds that are just a cation and an anion, and inorganic salts tend to be insoluble in most organic compounds. But silver nitrate is actually soluble in ethanol, and so we can make a solution with silver nitrate in an organic solvent. And if we take that solution of silver nitrate and put it in the presence of a halide, what's going to happen is that our solution of silver nitrate plus our halide is going to form some precipitants. And specifically, we're going to form a couple of silver salts which precipitate out of solution. So these are going to be solid, so they're going to precipitate out of solution. And this is going to work for chloride, bromide, and iodide. So we can use silver nitrate to qualitatively test for the presence of halides in solution. Now, how is this going to help us for our reaction? Well, what we're going to do is we're going to take an alkyl halide. So let's just get a generic alkyl halide here. Okay. Now, if we put that alkyl halide into solution, so let's just put it into solution in ethanol. Okay. So just for argument's sake, let's just take our alkyl halide, we'll make a solution of it in ethanol. Now what we notice about this halide that we have drawn is that it is tertiary. And if we have a tertiary halide, we've got a polar protic solvent, we're favoring or we're pushing towards an SN1 mechanism. And so what does that mean? Remember, the first step in an SN1 mechanism, at least in this instance, is going to be formation of our cation. And so what's going to happen is we're going to split off our halide. And so we're going to leave behind our cation, and our halide is going to form also. Now, if we add to this reaction some silver nitrate, okay, the silver nitrate's not really going to affect too much in the first step, right? We're still going to have to split off our halide, but now if we have our halide in solution and we bring in our silver ion, right, these are going to combine to form our silver salt and precipitate out of solution. Okay, so let's keep that in mind. Let's take a look at what happens if we would use a different halide. So now we have a primary halide. We're going to walk through the same steps here. So let's put this into solution, and what happens? The answer is probably nothing, because remember, if we tried to generate our cation, oops, I meant to draw that in red. If we try and generate our cation in the first step there, similar to what we did above, right, we would end up generating a primary carbocation, and that's simply not going to happen. So this is not going to happen here. If that cannot happen, that means we do not have any halide in solution. So if we add some silver nitrate to this, we should not expect to see any precipitant, because we did not put any X minus in there, right? No X minus got formed because we could not generate a stable carbocation. So we're going to use this idea of silver nitrate to check for the ability of this halide to form a cation, to pop off in solution there, to generate and leave a carbocation behind. Let's look at one more example of what we're going to be doing in experiment 19. So similar to what we discussed with our silver nitrate, we're going to be using sodium iodide to look at the reactivity of some of our halides. Now, sodium iodide is again a inorganic ionic compound, which these are typically not soluble in organic solvents, but sodium iodide is a very important exception. We can make a solution of sodium iodide in acetone, which is a good organic solvent. So if we make a solution of sodium iodide, now we've got sodium and iodide floating around as our separate ions. And what happens is, if we put our solution of sodium iodide in the presence of a halide, what's going to happen is our sodium is going to react with our halide, so our X, and precipitate out a solution here. Now X in this case is going to be F, Cl, and Br. So sodium fluoride, chloride, and bromide are insoluble in our organic solutions. So they're going to precipitate out of solution again. So we can use sodium iodide to check for the presence of certain halides in our organic solvents. So similar to what we did on the previous slide, right, if we have a halide here, right, we put this into solution. This time we're going to put it in acetone, right? We may at some point start to generate a carbocation. And then we generate our carbocation. We have our X minus there that gets formed, our halide. And if we do this reaction in the presence of sodium iodide, if that X that we started out with is anything except for an iodide, it's going to precipitate out, right? We're going to do this reaction here where the sodium will react with the X minus, and we form our, let me just get the right color here. We're going to form this as a solid which precipitates out. And then this is removed from our reaction, right? That X minus is now solid. It's not in solution. It can't participate in this reaction anymore. So what happens then? Well, what we have left over then, right, is our cation. And don't forget about this over here. Let me highlight it in orange. We've got our iodide. So what we didn't draw over here is that we had iodide also floating around, right? We made a solution of this. And now we can just kind of finish things up. Boom, right? We can put these two together, and we ended up putting an iodide in the presence of the halide that we started out with there. So this is a very common reaction that we use to swap one halide for an iodide. Now, why would we want to do that? Well, one, it can give us some information about the reactivity of our particular halide. We have to be able to make a carbocation or release our X minus there, our red one, to begin with before we can precipitate out our sodium halide. And two, remember, iodide is a very good leaving group. It is an extremely good leaving group. So if we're trying to change our reaction conditions, if we could only put an iodide in its place, we can speed up certain substitution reactions. So this is a way that we can kind of change our starting material, right? We can change our starting material here into something that's a little bit more reactive, right? So if we had, let's say, a chloride to begin with, right? If we had a chloride over here, let's see, if we said X is equal to Cl, now we have an iodide at the end, right? And so our reaction is going to be different where we use that iodide except for instead of that chloride. So this is a good way that we can behind the scenes swap one halide for the other. We're going to be analyzing the products that we make in our reaction by two methods. First is NMR, and there's a separate lecture for that that's online if you haven't listened to it yet. And the second is by gas chromatography. Now, gas chromatography works by taking our sample and passing it through a column at elevated temperature. And that column that we pass it through is going to help separate our mixture of compounds out. So let's look at a couple different parts here. First, we have a carrier gas. Now, our carrier gas is going to help push our sample through the column. So we're going to need something to push our sample through our column. That's our carrier gas. Our sample injector here at number 2, our sample injector is basically a heated block. We take our sample, we put it into the sample injector at a specific temperature. We want to take everything in our sample and turn it into a gas. So we need this to be hot enough to vaporize everything, but not too hot that it decomposes what we inject into it. So we need to know a little bit about what we're testing before we can actually use a gas chromatograph. So our sample injector turns everything into a gas, and once it's in a gas, it starts to pass through a column that I'm highlighting in orange. And that column is where the actual separation happens. So let's look at an example on the inside of, let me draw this a little bit bigger, at the inside of this column. So on the inside of this column, there are different coatings and substances that you can put in there. And we are going to change columns depending on what you want to analyze. Now, the way the separation works is, let's say that we inject a sample that has some purple and blue molecules in there. We turn on our carrier gas and it starts to push things down our column. And one way that separation happens is if we have a molecule that wants to interact with those substances on the side of the column more than it wants to interact with the carrier gas itself, these things are going to pass at a slower rate through the column than things that do not interact with the side of our column. At the end of the column, we have our detector, and we'll talk about that in just a second. So our detector there in green, we'll just put it. And so what happens is as we push our purple and blue through this column, maybe the purple is going to interact with the column more than the blue will, and so we're going to see the blue hit the detector before the purple, and we get a different signal for each one of those. Now, another thing that we need to pay attention to is, let me just clean this up for a second. It's not only how this molecule interacts with the column, it can also separate based off of molecular weight. So let's say that our purple molecules have a heavier weight than our blue do. As our carrier gas pushes these things through, the blue are going to go faster through the column, right? Because they're lighter, right? It's easier to push something that's lighter than heavy. So our blue might get separated from our purple based off of molecular weight. And so again, the blue is going to hit the detector before the purple will. This is all to say that our compounds are going to get separated by the properties of the compounds. So we have to know a little bit about the structure and the reactivity and the different properties of the blue and the purple samples that we put through our gas chromatogram to make a proper experiment to separate them. So we have to know a little bit about the properties of the molecules before we can use a gas chromatogram. So now that we understand a little bit about how a gas chromatograph separates our compounds, let's talk about how we can get some useful information out of that. So here we're going to be talking about this detector. Okay, so we have two types of detectors that we're going to use, and they are for different purposes. So depending on what we need to analyze, we might need to change our detector. The first that we can talk about is something known as a thermal conductivity detector. So a thermal conductivity detector, the name kind of says what this is going to be. We maintain our detector at a specific temperature, and the environment in that detector has a certain conductivity associated with it. Any change in that conductivity is going to get translated into a digital signal that we can read into a computer. So if we have a quick schematic here, right? So let's say we've got our detector here in purple. Okay, so our sample comes in at the bottom here. So sample at the bottom, just for instance. And then we have other ports here for gas that comes in or out to maintain the environment. Okay, so inside our thermal conductivity detector, there is, let's make this in purple, a filament. So similar to what you see in a light bulb, right? So let's say there's a filament there in green. So if we maintain our detector under an inert gas at a specific temperature, there's a certain conductivity associated with that. As our sample comes in, right? So as our sample comes in, it's going to change the conductivity of that filament. The conductivity of the filament is going to change because now we have more than just the inert gas that's inside our detector. So as the conductivity changes, right, the internal filament temperature is going to increase. Okay, the temperature increases, that means the resistance is going to increase. If the resistance of our filament increases, that means our voltage to that filament is going to have to increase also, and we can use that change in voltage of the filament to say that there is a signal from an incoming sample. Now keep this in mind. I don't need you to know exactly how the detector works. What I need you to pay attention to is that we detect a change in signal. So a change in signal, excuse me, I meant to say a change in voltage is our signal. And this is not specific to any one compound that we put in there. Any compound that we add into our detector is going to change the voltage, which is going to produce a signal. So the other detector that we have is something known as a flame ionization detector. And you're going to see some similarities here. So flame ionization detector. So if we have our sample box, right, it's got some ports for gases in and out. Our sample comes in at the bottom, just in our schematic, right? I'm just giving you guys an example. Now inside our flame ionization detector, we actually have a flame, right? We have a flame that's in here. We also have a electrode that's held as a positive electrode, right? So we've got a positive electrode that's sitting in our detector also. Now as our sample comes in, it's going to hit that flame, and our sample is going to break apart into different charged species. They're going to burn. They're going to change into this radical here, CHO plus an electron. So any organic sample that comes through is going to get burnt, and it turns into that CHO plus and an electron. Now our electron is going to get attracted to our positive end, right? That positive voltage that we have inside of that detector. And so as the electrons get attracted to that positive electrode, it's going to change the current, because we maintain that at a constant current. An electron gets attracted to it, and it's going to change the current of that electrode. And we can convert that into voltage, right? And that voltage is going to give us our signal. So again, at the end of the day here, right, we change a voltage and it gives us our signal. Now these detectors have different uses for different compounds and have different sensitivities. But the important thing that I want you to recognize is that in a flame ionization detector, we have to burn our sample. In a thermal conductivity detector, right, we just measure a change in voltage. The detectors in a gas chromatogram do not look at what compound is coming through there. So these are not for specific compounds. We have to add a known sample into our compound mixture to see where they come out in our gas chromatogram. So what that means is we have to know a little bit about what we expect to get formed and add that through our gas chromatogram to see where it shows up. And then we can make a distinction between which compounds are coming out in our signals. And so our voltage gets converted to signals, and that's the last thing here that we see in light blue, right? We tend to see little spikes on a graph. So let's zoom in on here just a little bit, and let's look a little bit at what's going on. We're going to see a graph. On one side we have intensity. So our y-axis is intensity, the other one is time. Okay, so we're going to start at time 0, right? Time 0, nothing's hitting our detector. Eventually something's going to hit our detector. We see a spike. We might see another spike, right? And another spike, right? So these individual spikes are the signals from the detector that say, hey, something is coming through or changing the voltage. If you remember on the previous slide, we had purple, right? And we had blue things that are coming through. So hopefully if we have our gas chromatogram set right, we would see one spike for blue and one spike for purple. Now, for those of you guys still paying attention, we notice we still have that one spike that's out here. Now we have to inject our blue and purple using a solvent. So our solvent that we use to inject these with is also going to show up as a spike. So don't forget about that. And remember, the key part here is how do we know which one's purple and blue? That's based off of running a known sample through there and seeing where it shows up. And then matching the retention time, the time that we have in our gas chromatogram. So in conclusion, for this experiment, you have to be prepared. Thoroughly read these directions. There's a lot of very specific instructions. There's some that are time-based, and so we have to know what we're doing before you come in here. Otherwise, you might spend too much time. It's going to throw off your results. So along with that, make sure you have the appropriate sketches of your setups, right? Know what you're doing before you come in here. Spend your time doing it properly. Work efficiently. There's quite a few experiments and setups that you need to do, so plan your time wisely before you come in, otherwise you might run out of time. As with all things, but especially here, keep your area and your glassware clean. Spend some time cleaning your glassware before you start, otherwise, again, you're going to throw off your results. Now, at the time that I'm recording this, our gas chromatograms are still in Buehler Hall. Now, we're not going to make you guys walk over to Buehler to run your samples, so your gas chromatographs might be run by your TA. So at the end, you're going to be capping these up, giving them to your TA, and they're going to run the GC for you. If everything goes as planned, we might have the GCs for you guys to use in the lab itself. So fingers crossed, I hope that we have an opportunity to use the gas chromatographs that we have ordered for you guys. I think that'll be a fun experience. But whether we do have the gas chromatographs or not, you guys will be running NMR. So brush up on your NMR. You will be collecting your NMRs on the samples that you make also.